Hello, my name is Matteo Benedetti.
And my name is Matthew Jenkins.
And this is our project.
Our project, the balance tank, keeps a central platform level at all times, including when driving over uneven terrain. This is accomplished by sensing how much the platform is rotating with gyroscopes and counteracting this rotation with motors. But it doesn't just balance in one dimension. By having two gyroscopes, one on the pitch axis and one on the roll axis, we can balance the platform in two dimensions. The platform is also suspended in the air and balanced so that it can rotate with as little resistance as possible. We also have these fancy gearboxes that give the motors more accuracy in their movements as well as more torque. The motors are connected to the gearboxes, which are then connected to each respective axis of rotation. The pitch motor shown here is connected at 90 degrees to make it more compact. Shown here is the front section of the bot, with the EV3, a push sensor, and a large motor connected to wheels to drive the bot forward. My wonderful partner Matteo will now demonstrate how to calibrate the platform. When we run the program, it will turn the platform to the left by about 20 degrees. We then hold the button until the proper pitch angle is reached. Same for the roll, and then press the button again to turn on the motor. From this chosen starting position, even when the tank is rotating, the platform will remain completely level with the ground. Just look at how level that is. Perfect. But you might be asking, what's the point? Why have all these complex gears when I can just strap a weight to the bottom? Well, the calibration isn't just because we're bad at coding. It also gives the freedom to choose any initial angle for the platform to stay at. Here we're doing the same starting calibration sequence, but we'll just choose an awful angle. How about this one? And this one. The robot doesn't care about your life decisions. That one works just as well. No matter what initial angle you pick, the platform will stay at that angle. We'll now move on to some terrain testing, starting with a downhill ramp. Pay special attention to the angle of the platform. As you can see, the weight distribution is not ideal, but the platform stayed mostly level, even with these harsher terrain conditions. Next, we'll test the roll axis of the platform by raising one side of the tank. As we can see, on a slow incline, the platform remains level. But what about a sudden drop? The drop shook it up a bit, but even then, the platform stays level.
This next clip demonstrates the unfortunate limitations of our vehicle. The traction of our wheels really limits the steepness of slopes the vehicle can go on. While the balancing mechanic can handle these slopes and angles, our wheels simply cannot. Additionally, sudden drop-offs can affect the balancing of the motors by either impeding or forcing them to turn, offsetting the balance, as you can see here. In this part, we see some of the data collected by the gyroscope that help the robot make its decisions with regard to balancing. The right graph shows the rate of angle change as a function of time for the roll gyro. The graph appears sinusoidally as we roll the vehicle. Similarly, the left graph shows the rate of angle change versus time for the pitch gyro. This graph also appears sinusoidally on the left graph as we pitch the vehicle. Notice how the motor stays level as we move the chassis. Now finally, a tour of our LabVIEW code. This code is split up into four main parts, the first of which is the initialization. We first reset the motor encoder, then we rotate for 1 second, then we kill the engine. Next, we set the pitch offset. When we hold down the button, the pitch motor rotates at constant speed. When we release the button, at our desired angle, we kill the engine and move on. Finally, we set the roll offset. If we hold down the button, the roll motor will oscillate between its maximum range until we release the button at our desired roll angle. When that happens, we kill the engine and move on. After we finish initializing, we move on to the meat of our code. We start by setting the large motor to a constant speed to drive forward. Next, we monitor the rate at which the pitch gyro changes and set the speed of the pitch motor opposite that, so the motor undoes, in a sense, what the environment wants to do to our platform. After that, we see our diagnostic graphs from the front panel, receiving data from either of our gyroscopes and plotting them against time. Here we see some initialization of the time and the arrays. Finally, here at the bottom, we have the roll analog to the pitch motor code we saw above. If the gyro detects a change in angle, the motor will run in the opposite direction to correct it.